sklearnensembleVotingRegressor voting regressor. Description: the voting regressor in sklearn is a powerful ensemble learning method for combining multiple regression models to improve prediction accuracy. It leverages the strengths of different models by averaging their individual predictions, effectively mitigating the weaknesses of any single model. This process typically results in a more robust and accurate prediction compared to using any single model alone. Inputs: estimators. This is a list of trained regression models that the voting regressor will combine. Each model should be an instance of a regression estimator like linear regression, random forest regressor, or gradient boosting regressor. Weights optional. This parameter allows you to specify weights for each individual estimator. By default, all estimators are weighted equally. However, if you have prior knowledge about the relative performance of your models, you can use weights to favor certain estimators over others. Outputs: predictions. The voting regressor outputs predictions for new data points. These predictions are based on a combination of predictions from the individual models in the ensemble. Steps: training. The voting regressor does not perform any independent training. It simply takes already trained regression models as input. Prediction. When predicting, the voting regressor feeds the input data to each individual estimator in the ensemble. It then combines the predictions from each estimator according to the specified weighing scheme. Metrics: R-squared. This metric measures how well the model explains the variance in the target variable. A higher R-squared value indicates a better fit. Mean squared error (MSE). This metric quantifies the average squared difference between the predicted and actual values. A lower MSE indicates better accuracy. Root mean squared error (RMSE). This is the square root of MSE and provides a measure of the average difference between the predicted and actual values. Lower RMSE values are preferred. Visualization plots. Residual plots. Residual plots visualize the difference between predicted and actual values. This can help identify patterns in the errors and assess the model's assumptions. Feature importance plots for some models, e.g., random forests. Feature importance plots can be generated to understand the relative contribution of different features to the prediction. Learning curves. Learning curves can be plotted to assess how the model's performance changes with the amount of training data. Fine-tune parameters. Estimators experiment with different regression models, e.g., linear models, decision trees, ensemble methods to find the best combination for your specific problem. Weights. Adjust the weights assigned to each estimator to fine-tune the ensemble's performance. You can use grid search or other hyperparameter optimization techniques to find the optimal weights. Uncertainty methods. Confidence intervals. While not directly implemented within voting regressor, you can obtain confidence intervals for the combined prediction by analyzing the individual confidence intervals of the estimators. Challenges and fixes. Challenge 1: overfitting. If the individual models are overfitted to the training data, the voting regressor can inherit this overfitting behavior. Sample use case that resulted in challenge 1: a voting regressor is used with multiple decision tree models trained on a small dataset. The individual trees overfit to the training data, resulting in poor generalization performance on unseen data. Fixes to challenge 1: use regularization techniques, e.g., L1 or L2 regularization on the individual models to prevent overfitting. Utilize ensemble methods with built-in overfitting mitigation, such as random forests or gradient boosting. Consider using a validation set during training to monitor model performance and detect overfitting. Challenge 2: bias in ensemble. If the individual models have significant biases, the voting regressor may not be able to correct for them, leading to biased predictions. Sample use case that resulted in challenge to a voting regressor is used with multiple linear models, each exhibiting a different bias in the data. The ensemble inherits these biases, resulting in systematically inaccurate predictions. Fixes to challenge 2. Select individual models with different biases to balance out their combined effect. Use techniques like data preprocessing to correct for known biases in the data before training the models. Explore alternative ensemble methods that are less prone to bias, such as stacked ensembles or bagging.